In this video, we're going to try to dissect the range of behaviors that we can find or that will be exhibited by a damped spring mass system. And what we're going to do is keep K and M constant and gradually just increase the damping coefficient from no friction whatsoever to just a little bit of friction to more to heavily damped. And we're going to see how that affects the mathematical forms of the solution and why. Remembering that the equation we start with is just Newton's second law, sum of the forces, is equal to mass times acceleration. Spring force, damping force, and that's all that's in play. When we rearrange that, we got all positive coefficients on one side equaling 0, and when we made our assumption about e to the lambda t being what our x form should look like, we always got a quadratic in lambda, and that quadratic in lambda can always be solved by using the quadratic formula. That's going to be our gateway to understanding this here. So here's c increasing. And if c is really, really big, and by big I mean larger than this other term under the square root in the quadratic formula. Why? Well, if c is big enough, we get a positive c squared minus 4km. And if that's the case, then we end up with lambda is equaling something real plus something real. So these lambda values are going to be negative somethings, because we're going to do negative, and as it turns out, this is always going to be smaller in scale than c itself. Do some math on that if you like too, but I'm going to write them explicitly as negative lambda 1 and negative lambda 2 to reinforce that they are going to be negative quantities. And the form of the solution there is e to the negative lambda 1t, e to the negative lambda 1 lambda 2t, and that is going to be two exponential decays. No oscillations. So I'm just going to erase that briefly. That's the form. This is going to be no oscillations and graphs that head down towards 0 over time. That's all they do, with exponential decays specifically. That is one example that we saw previously. Let's go to the other extreme where we have no damping at all. If we have no damping at all, then we just get the square root of minus 4km. Now the 4 seems weird until you remember that it's all dividing by 2 m's. And when you work that out, you're going to get a lambda of plus or minus the square root of k over m, with the square roots and regular powers and the 4's and the 2's all canceling. We get our square root of plus or minus k over m square rooted, and that leads to, oh wait, one ingredient missing, times I. Because this negative sign is in the square root here, the lambdas that we get are imaginary, and imaginary exponentials end up looking like cos and sine. All right, that is the form that we're going to end up with, but it's not really a description, so we're going to describe that. That is going to be oscillations that are undamped or constant amplitude. These are the no friction, no reason for energy loss, and so these oscillations are going to continue on forever. In the medium ground, what we're going to get is something where the square root of c squared minus 4km all over 2m, this whole thing is still negative. So we're going to end up there with lambda equals a plus or minus some imaginary coefficient, because there's going to be a negative value inside the square root, but there's also going to be a negative real part. And we're going to get that as solutions like e to the at, technically it should be negative a because it'll be a negative coefficient, negative at, tweaking that, there we go, negative at cos bt sine bt, and we call those damped oscillations. They still oscillate, but the amplitude is going to decrease with time. Now, you'll notice there's one value left off in the middle, and that is this one here. Well, what happens at the transition? Here we have c squared less than 4km. Here it's c squared greater than, well, of course, there's going to be a transition when those two things are actually equal to one another. What happens there is we get a 0 value for everything under the square root, and which means we actually get lambda equal to the same thing twice. In practice, this is not very exciting because it never happens in practice. This is a mathematical transition point curiosity, but it does mark the transition between two regimes, so it does have a nice name that we conceptually think about this as critical damping. With the idea being, if we have no damping, we get oscillations that go forever. As we dial up a little bit of friction, we get damped oscillations. They fade and fade with time. The critical damping is the damping level at which we switch over from having oscillations at all to having no oscillations. And it's just a mathematical transition point that is defined here as some relationship between the spring, mass, and damping coefficients. Often in mechanical systems, we'll look for this. If you think about car shock absorbers, you don't want shock absorbers, generally speaking, that keep oscillating for a long time, but you also don't want them to be really, really harsh in how they damp motion, because that actually makes it feel like less smooth. So in a lot of scenarios, you're looking for that critical damping, that transition just between where you get oscillations and where you stop getting oscillations. It might help to visualize this a little bit first, though, to see what these graphs look like, rather than just the mathematics. All right, so the undamped scenario is what we saw way back in the beginning. Cos of square root of k over mt, or sine square root of k over mt. If damping isn't there, the solution's easier to solve for. We get all sorts of nice behaviors. I'm just trying to make this as even as possible. Here we go, like so. Key property here is that the amplitude is constant. In an undamped scenario, we just have a mass that moves up and down and up and down and up and down forever, always with the same amplitude. In the damped scenario, we get the same basic idea. We still get oscillations. The difference is when we start at a peak here, we are not going to necessarily get all the way back down to the same point on the next cycle. We're going to see something like this. So oscillations are happening, but the amplitude decreases with time. And those look like e to the minus a cos of bt at and e to the negative at sine bt's. So there are sines and cosines, so there are oscillations, but there's also a multiplier for the amplitude that dictates that it decreases over time. Overdamped, we have two negative exponentials. And it's hard to tease out those two negative exponentials, pardon me, like lambda 2t. It starts high, and then it just goes down, and if you have a combination of them, you really can't tell by eye. It's going to look like an exponential decay because both of these eventually head towards zero. That describes overdamped in the sense that it's so heavily damped that we don't get what we usually think of as normal for a spring mass system, which is oscillations. Overdamped, no oscillations. And the critically damped turns out to be the same thing here, but again, we're going to get some fun linear algebra when you do this in your differential equation class. You do not need to memorize this formula or this solution, but it turns out what we get is the same exponential twice, but to make them a little bit different, we end up multiplying by t. Again, you'll see this in second year, don't sweat it for now. In practice, it looks essentially identical to the damped. The difference is that the damped might actually decrease less quickly because it's so resistant to motion. Imagine again those sort of heavy doors that you see in entering school buildings or shopping buildings. If they're so heavily damped, it's just so hard to push at all that you might have things decreasing for a long period of time. The critically damped, in some sense, is the curve that goes down towards zero the fastest while still having no oscillations. It's also worth noting, again, it can bounce once. Like if you push it, it might overshoot once and then damp down. It just will not ever cross an infinite number of times like these two up here would. Okay. Next up, some demonstrations. We're going to explore how this all works through a MATLAB simulation. And again, remembering that we're looking for predictions of motion. We're going to see that in the next coming videos where you can try to interpret or parse this effect of increasing damping on the behaviors of the solutions and the kinds of graphical behaviors we get back or the motions that we get back. And we'll try to explore that a little more interactively with software.